Hi everyone. Today we're going to be looking at real-life problems that can be modeled with trigonometric functions. We need to first identify and define what frequency is and how that relates to our period. So our frequency is the periodic nature of trigonometric functions, actually makes them really useful for modeling. Anytime you have an oscillating motion or repeating pattern that occurs in real life. So some examples are sound waves, the motion of a pendulum, and the seasons of the year. In these situations, you have the reciprocal of the period is what we call frequency. So this gives you the number of cycles per unit of time. We have pretty much our definition. So your frequency is equal to the reciprocal of period, which is 1 over period. You can take that actually a step further and say, well, I know what my period equation is. That's just 2 pi divided by b. So we know the frequency is just a reciprocal of our period. So that would just be b divided by 2 pi. All right, we're going to make sure we know this situation. For frequency, we're going to have our first example. We've got a sound consisting of a single frequency is called a pure tone. An odometer produces pure tones to test a person's auditory functions. An odometer produces a pure tone with a frequency of, so they're giving you the frequency in cycles per second. The maximum pressure produced by the pure tone is 2 millipascals. We're going to write and graph a sine model that gives us the pressure P as a function of time in seconds. So we go to our sine function. We've got pressure as it relates to time is our variable P, and that's equal to A, which is the maximum pressure, which we know is our amplitude, multiplied by sine times b, which we're going to have to solve for. We don't know our b value, and t is in seconds. What we have to begin with, I'm going to define a few things. So we have our frequency and our max pressure. Looking at our graph, I get the two along the y-axis because of our max pressure. All right, so we have our max and our min. All right, now we can actually get our period from the information from the word problem looking at the frequency. So we know the frequency is 2000 hertz, so our period is just a reciprocal of our frequency. So our period would have to be 1 over 2000, which is the full length of one cycle of your sine. So 1 over 2000 could be labeled all the way for this critical point. And then you can get your other couple critical points, like your other x-intercept, because your middle x-intercept will be halfway between 0 and 1 over 2000, which would be 1 over 4000. And then your other critical points between 0 and 1 over 4000, halfway between that is your 1 over 8000. And you can do the same idea over for your other critical point. Halfway between 1 over 4000 and 1 over 2000 would just be 3 over 8000. All right, that's not doing much help to write the equation because we need to find our b value. So looking for our b value, we're going to use what we talked about in the very beginning and talk about our frequency. And so our frequency is equal to b over 2 pi. So let's use that. Frequency equals your b divided by 2 pi. which plug in your frequency. You've got 2000 hertz is equal to our b, which is what we're looking for to write our equation, divided by 2 pi. I treat it as like a cross multiplying situation. So you've got b is equal to 4000 pi. Okay, we're going to hold on to that information. We got to look for our amplitude, and because we had a maximum pressure, the max height of your graph is going to be up at that 2, and we know our amplitude is from our midline, which would be y equals 0, all the way up to the max height. So our amp is 2. And that's enough information for us to write our equation. You've got P is equal to our amplitude 2 and sine multiplied by 4000 pi x. All right. One quick note that I didn't point out in the beginning, maybe you're asking, why did I choose sine? Why did I choose the sine function as opposed to cosine? Well, that was given in the problem. So write and graph a sine function or a sine model. Pay attention as you go through the problems. It's a lot easier in this case to write the sine function as opposed to rewriting this as a phase shift with a cosine function. You're going to do a lot more work if you did that. All right, so let's get into writing more trig functions. So graphs of sine and cosine functions are actually also called sinusoids. One method to write a sine or cosine function that models a sinusoid is to write and find the values of a, b, h, and k for, here's your general forms. These are as ugly forms as they can get. You know absolute value of a is the amplitude. You've got your period is 2 pi over b, as long as b is greater than 0. And h is a horizontal shift, and k is a vertical shift. So in example 2, we need to write this function as either a function of sine or cosine. I'm going to warn you, pick the one that's easier. Okay, yes, you can write every sine function as a phase shift of cosine function, so they're interchangeable, correct? If we were taking in-class tests, I would be having a bunch of options as answers for these, one as sine and one as cosine most likely. All right, so let's see, what am I going to pick? I first look at the very beginning of the graph. I go find my y-intercept. And I go, does that look like, I find one period. So we go, it starts in the middle, goes high, here's another critical point, and then goes low, and then one full cycle, oops, too far, goes up to, back to the midline. Oops. All right, so I found kind of like my 5 key points here. If your function starts in the middle, goes like this, we know it's sine, or you can write it easiest as sine. If it starts high, goes low, and loops up, you've got a cosine situation. All right, so let's figure out what we need to find here. We need our amplitude. So where do you want to start? We can go for our period. You can just find all your A, B, and H, and K. I'll start with my amplitude. I take a look. I find the middle of my graph. You can find the midline any way you want it, or any way you want to. One option is to take your max value plus your min value and divide by 2, or find the middle. Whoops, get out of here. That'll give you your midline. So our max, now look at the coordinates. Sometimes these graphs are a little tricky to see. So you've got a max of 5 and a minimum value of -1 and divide by 2. So you've got 4 divided by 2, which we know is 2. So y is equal to 2 is your midline, which you could probably just figure out any means possible. Now let's look for our period. All right, period. I want to look and see how long that pink part of the graph is. So I see a pi. So backtrailing, that little tick would be pi. Oh, pi over 2. Sorry. And then halfway between 0 and pi over 2 is, of course, pi over 4. So actually that full one cycle is from 0 to pi over 2. So we know our period is equal to pi over 2. Now we need to find our b value. So use your formula for your period. Pi over 2 is equal to 2 pi divided by b. And give it a little cross multiplying. We got b times pi is equal to 4 pi, divide by pi, and you have yourself b is equal to 4. I'm going to box that. I need that. Oh, I found the midline, but I didn't actually find my amplitude. Let's go back to that real fast. So our amplitude, the height down to the midline, our midline is 2, count up to 5, so our amplitude is equal to 3. All right, and that's pretty much all we need. Let's write our equation. So put it all together. We've got y is equal to our general form a times sine of b times x minus h plus k. Now I don't actually have any h or k. Well, I have a k. I have a shift up of 2, right? So up 2 of our graph, but I don't have an h value because there's no phase shift. Our first critical value, let me get a highlighter so you can see what I'm talking about. Our first critical value, I mean, that's the beginning of our sine function right there. So don't worry about any phase shift here. Drop everything in. You know y is equal to your amplitude, 3, sine of your b value of 4, multiplied by x minus 0. I'll leave that in there. And then our whole graph got shifted up 2 because we have a midline. And simplify it a little bit. We've got 3 sine of 4x plus 2. All right, we did it. Now let's look at an extra example 2. This is going to be a cosine function, all right? And I see it as a cosine function because I want to find my beginning critical values. So look at your y-intercept. It's technically up at 13. It's halfway between, it's counting by 2s, just as a heads up. 6, 4, 2, all the way down, keep going, -2, -4. And then those low values, our minimum values, are at -5. All right, so my graph starts up all the way at 13, and then it goes low, and then hits a minimum value, and then turns all the way up. And that is one full cycle of what looks to be cosine. All right, so I don't want to rewrite this as a phase shift of sine, even though you could. That's just tedious and kind of a pain. All right, so let's find our midline. I think that would be the best option to do first. So our midline. Okay, we're going to take our max plus our min, divide by 2. So you get your maximum of 13, subtract 5, divide by 2 is equal to 8 over 2, which is 4. All right, so our midline is right at y equals 4. All right, we can find our maximum from there. So from 4, how far is it to get to 13? That's your amplitude. So amplitude is equal to 9. All right, let's see. So we have our shift up 4, amplitude 9. Let's go and talk about our period. So our graph, one full cycle, ends at pi over 4. So our period is equal to pi divided by 4. Let's find our b value. So use your 2 pi divided by your b value is equal to pi over 4. Cross multiply. Pi b is equal to 8 pi. So b is equal to 8. Box that. All right, and that's pretty much all we need. There's no phase shift because it's our graph, our cosine, one period started on the high. So we've got y is equal to a times cosine of b times x minus h, no phase shift, so that'll zero out, and plus k. So drop in y is equal to your amplitude, 9, cosine, our b value is 8, multiplied by x minus 0, and plus our midline is 4, so plus 4. Simplify it a little bit, 9 times cosine of 8x plus 4. All right, so our jump rope problem. Example 3, your best course of action is to draw your graph as you go. All right, so I'll break it all down for you. You've got 2 people swinging jump ropes as shown in the diagram. The highest point of the middle of the rope is 75 inches above the ground. So you've got a maximum of 75 inches above the ground here. And then the lowest point is 3 inches all the way down here. And that is 3 inches above the ground. The rope makes 2 revolutions per second. We're going to write a model for the height in inches of a rope as a function of time in seconds, given that the rope is at its lowest point when t equals 0. All right, let's just try to graph a little bit of this situation. All right, we've got time as our x-axis, and we've got height above the ground on our y-axis. So you've got the graph goes and starts at t equals 0 at 3 inches above the ground. Let's talk about our period. The problem says the rope makes 2 revolutions per second. So on my x-axis for my time, I know that in this full 1 second, it's going to make 2 revolutions. It's going to spin twice around. All right, so 1 revolution would be half a second. So that is going to be our period. So 0.5 of a second. That is 1 revolution. So I'm going to start at t equals 0, and my graph is going to be all the way back down at 0.5 seconds. Now it's going to have exactly halfway between time equals 0 and time equals 0.5. At about 0.25, you're going to be at a max height of 75 inches. All right, so you'll see it's going to cross the midline halfway between those 2 critical values. So this, to me, I look at it as a cosine function. I go my normal cosine. That's a little wonky, sorry. So cosine starts high, goes low, and then goes back high, right? But what would a reflection of that cosine be? I'm going to go over to the right, and negative cosine would just be low, gets high, and then ends low again, right? So I'm actually going to I'm going to choose to write this function as a function of cosine instead of sine, because of my y-intercept is actually a low point. All right, let me get some more room. Let me erase that. Okay, so let's see, what can we find? Let's find our amplitude. So our amplitude, take your, in this case, you're going to go and take your high, your max, and subtract away the minimum since it's all above the x-axis, and divide by 2. So 75 minus 3, divide by 2. That'll be an amplitude of 36. Okay, so this one's kind of tricky because you have to apply that amplitude. So from here, 75 to the midline, which we don't know where it is going to be a distance of 36. And same story, from here to here is 36. Now, the trick to this is it started 3 inches above the ground. So take that amplitude of 36 and add in that 3 inches above the ground, and you'll get your midline. So let me erase a little bit of this. Midline would be at y is equal to your 36 plus your 6 would be 39. Okay, and let's take a look. While we're talking about that midline, we know the midline is related to our amplitude, our a value in the function that we're going to be plugging in. Now this is a reflection of the cosine function, right? So we're going to use our a as a negative 36. It's a reflection across that old x-axis. So I'm going to box that. All right, and now let's get our b value. So find our b value. Okay, we're going to go to our period. We figured out our period was equal to 0.5. So then we're going to set that equal to 2 pi divided by b to find our b value. It's equal to 0.5. Cross multiply. So 0.5 b is equal to 2 pi. So your b value would just be 4 pi. Box that. And that's pretty much all we need there. So we get our h of t is equal to our negative 36, and that comes from our amplitude and the fact that it's a reflection of the cosine parent graph. And we chose cosine, and then our b value is 4 pi multiplied by our time. Now we don't have a phase shift for this cosine function, so we don't have to worry about an h or anything. And then it got shifted. Our midline is now at 39. All right, that problem's pretty tough. Hang in there and look, just find your A, your B, and sometimes you'll be looking for a phase shift if you need to. Now, at this point, go grab your graphing calculator. I'll show you how to do some of this on your graphing calculator. Example 4, we're actually going to use, hey, remember when we used linear regression, quadratic regression, and some of the other regression functions in your calculator? Well, it's the same old thing, just now we can use a sinusoidal regression. Now, The table shows the number n of hours in daylight in Denver, Colorado, and the 15th day of the month, where t is equal to 1, represents January. So we've got January is the first, February is our second month, March, so on and so forth. Okay, write a model that gives n as a function of t and interpret the period of its graph. All right, so turn your graphing calculator on, follow these steps, and get all that data into your graphing calculator. So make sure you turn your stat plot on, and then you're going to go stat edit and enter all of your data into your L1 and L2. And you might have to fix your window, or you can use your zoom stat number 9 to get the graph or the stat plot. All right, so at that point, you should have what looks to be a sine regression. So your graphing calculator is going to use sine regression, and that is on stat calc. Sine regression is C. I don't know if I got that. Okay, so let's add that. Stat, and then jump over to calc, and then go down to sine regression. And that is C. So C. Okay, and you're going to hit enter, and you're going to calculate. And you should get this information at the top box. So they're telling you your A value is 2.76, your B value is 0.51, C is negative 1.59, and your D value is 12.13. All right, and you can write the full function, y equals 2.76, sine of 0.51, I used 11t, minus 1.59, plus your midline of 12.13. Now you can take a look and, just as a heads up, make sure right now that your calculator is in radians, or when you enter this function back into your graphing calculator in your y equals, it'll give you something different if you're in degrees, okay? So drop that equation back into y equals button, and you should get this nice little sine regression line or curve. All right, and that's about it for today. See you guys soon.